he asked this question, how can we fix this problem, and it turns out people worked on it. I will not tell you the derivation for KPZ equation. So, it is more realistic, this equation which I am going to describe now is more realistic, which is derived in this book, and this equation gives you reasonable answers, okay. In fact, better answers for many experiments, and this is a very famous paper which has huge citations, okay. I mean, a lot of people following. So, 1986, okay, you can see it is a very old work, 40-year-old work roughly. So, the equation which we are going to use now, I am not deriving it, it is not really a course on surface growth. So, so we have a new term, this is a nonlinear term, lambda by 2, lambda is a constant, grad h squared, okay. Grad h is a gradient, okay. So, basically if you look at the proof, so this is a surface, then the surface roughness, basically this is a velocity v of t, so it is derived in a more realistic manner, okay. So, and there is a nonlinear term comes. Now, it turns out how many parameters we got, there is a new parameter, new is the viscosity which as before, there is a nonlinear term lambda, a coefficient, okay, there is a prefactor, and there is a same noise we will use. So, there is a factor d, noise correlation which is d also comes into play. Now, this equation analysis because of nonlinearity is not easy, and we will use some field theory tools, okay. So, one thing to keep in mind that lambda is not renormalized, okay. So, I am going to, so let us do the scaling argument, okay. Let us just do first simple scaling argument, you will see some hint. Okay, so I did this before, so basically this term and this term and this terms were there before, but this new term has come. So, I am just going to copy that from my earlier notes, dH by dt equal to nu b to the power z minus 2, no sorry, this alpha minus z plus lambda by 2. So, grad will give me 1 by 1, grad is 1 by length, no. So, b minus 2 and h will give me 2 alpha, correct. So, that is the term coming from h squared is 2 alpha and that, and this term will give me b to the power minus d plus z by 2, same as before, except I got a new term here, okay. So, if I keep new lambda same, not change it, then what do I get? Nu b to the power. So, sorry, this is 2 minus z not alpha minus z, 2 minus z, no. So, that grad will give me minus 2, sorry, minus 2, that will give minus 2 and h is alpha, what I am doing, minus 2 plus alpha. So, alpha alpha cancels and I get z minus 2, this we did it before, z minus 2, and the new term is lambda by 2 b, 1 alpha cancel with this alpha and I get alpha plus z minus 2, and then the last term is b minus z and this, so this becomes z by 2 minus alpha minus d by 2 eta, okay. So, from this relation what do I get? Alpha plus z equal to 2, correct. Now, what will I get from here? Z equal to 2, but then alpha is 0, right, this is a problem. Alpha 0 means roughness does not change with L, okay. So, what is the problem? The problem is assuming that nu is a constant, okay. Nu can change with b, okay, that is renormalization. when I change my system size, my nu also will change, and it is not new. I mean, we have seen it for turbulence. The viscosity is different at different lengths. Okay. So, the nu being constant is a gross assumption for nonlinear problem. Okay. So, I have to renormalize nu. Okay. So, this nu is some function of B, and that will give us the correct result, which I am going to derive it in fact. Now, it turns out that D, which is correlation of eta, also is function of P. Okay. D also gets renormalized, but interestingly lambda is not renormalized. Okay. Lambda is not renormalized. Why is lambda not renormalized? In fact, it is the Galilean invariance which I proved for Navier-Stokes. It works exactly for this problem too. Okay. So, you see the motivation that we need to renormalize these coefficients to get proper answer. Okay. So, basically we need to renormalize these factors. So, this is my equation, KPZ equation. Okay, I think I am losing. I hope everybody is following me. Okay. So, in fact, let me prove it how well. I am not going to prove the in full detail, but I will show you how lambda remains unchanged for RG. There are two methods, but one simple method is by Galilean invariance. So, it turns out if I write grad h equal to velocity u, velocity vector. Okay. So, I can take gradient of this equation, then I get a new equation, and that equation is this equation, nu grad square u plus lambda u dot grad u plus gradient of eta. But gradient eta is also a noise, some new noise, you can call it zeta if you like. So, this equation, anyone knows what this equation is? Navier-Stokes equation without pressure gradient, right? And this equation should also respect Galilean invariance, right? I mean, the way we did Navier-Stokes. So, this is a Navier-Stokes equation with pressure being 0. So, it should respect Galilean invariance. So, the lambda should not change. That is a simple argument. Okay, everybody is with me. So, lambda fortunately is not renormalized or does not change with RG. So, constant lambda is not renormalized due to Galilean invariance, but we need to renormalize nu and d, these two coefficients. Okay. Now, let me just quickly do it. I am not sure whether all of it will be clear, but let us do this steps. Okay. So, we will write down the Green's function and correlation function for the linear part. So, perturbation I am going to use so by this Galilean invariance we show that lambda is not changing under RG. Oops. Okay, but we need to renormalize nu and d. Okay, so that these two things, and it is very similar to what I told about hydrodynamics. No, this nu and d. Well, we did not, for in my calculation I did not renormalize d, but Jacob-Herzog as well as the functional RG which I was talking about for generating function, we normalize nu and d. This is nu. Okay, this is nu. So, what do I do? We follow, this is KPZ, the famous paper. So, we write down Green's function for G naught. Okay. So, let us write G naught. So, in Fourier space, do I have Fourier space thing? Yeah. So, these are my Fourier space equation. Is it you understand what it is? So, this term is coming here, this term nu k squared, right, that is term there, this eta is right here, and this grad h squared is a non-linear term. So, that becomes a convolution, right. So, I lambda by 2 which is missing here, and the convolution is product becomes a sum in Fourier space. So, this is h p omega q, no, this is omega p, and this is q omega q. Omega is a frequency, so I have two different frequencies. So, this grad h gives you one p, gradient gives you a wave number, no. Gradient of f in Fourier space becomes I k Fourier transform of f of k. So, since I am using p as a variable, then that gives me I p from one gradient. Other gradient will give me I q, which is coming from here and is integrated. Okay. So, this is what we get for these two for the nonlinear term. Now, idea is quite simple actually. So, we write the Feynman diagram. This one is h of p and h of q, and this is a vortex. This is a vortex. Okay. So, let us rewrite, well, basically let us compute it to first order in perturbation. Right now, I written this, no, I mean this is what I have it here. So, please recall your earlier calculations, what I did. So, I write this as a Green's function, expand h q as a Green's function times nonlinear term. This is my G naught inverse by definition. So, I take these to the right hand side and multiply by the full right hand side term. Yes. So, we write this as a Green's function G of q, one C of p is there. Now, what do we get this? Well, basically focus on the nonlinear term. I get one h and one h here. Yes. So, this h of p, this should be h of minus p to give you non-zero value, right. I mean this is we did it before, and what will this be by conservation of momentum or this wave number. Here also the momentum must be conserved. So, q equal to minus p, and what should that be? Plus k, right. So, this should be h of k. So, if you put k, then p plus q, p minus p will go to the left and p plus q is k. So, you see this term is my bubble or self energy diagram that is going to correct this viscosity. This is precisely what I did before. Yes. Follow me or no? How many of you follow me? Please raise your hand. This is precisely I did for hydrodynamic turbulence. So, this diagram I just Green's function, and these are two u's coming from here. So, G of q, no, I mean instead of h of k I write h of q. So, this G inverse will go to the right, that becomes G, and this will replace p will be replaced by r and s. So, we write h of q is Green's function of q. So, I put a 4 vector like that. Okay. So, that is for omega G of q, and right hand side will be integral u of r, h of r and h of s, 4 vector. Okay. Now, so this comes with this h of r and this is h of s, but h of r will, I need to multiply h of p, and they will give me non-zero value only when r equal to minus p, right, because of this noise term. H is also fluctuating, because eta is fluctuating, h is also fluctuating. So, the r must be equal to minus p, right, that is what we did before. I mean this part you should remember, and s will be by conservation of by this momentum stuff, this it should be h of k. Okay. So, that is what we get. Now, I need to compute this, but compared to, so in my fluid turbulence lecture I put h of p, this is correlation C of p, and I wrote from Kolmogorov theory, but this is not done here. We write in terms of noise. Now, I forgot to say one more thing, I think it is okay. So, this is a Green's function, and correlation function I discussed before. So, this is what we will do. So, new normalization, this is what I wanted to say. So, I need to separate into less and greater. Okay. So, remember we are going to see the effect of this on nu. So, I write minus I omega plus nu k squared h less of, I write is a 4 vector. Huh? So, k omega k hat is k omega, that is a shorthand. So, right hand side will involve h less p h less of q plus eta less, but it has other terms too, greater 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 less, right. So, we will have term h less p h greater q and interchange, and the next term is h greater p h greater q. This equation is same as before, this becomes 0, this is non-zero term, and that is going to correct nu, okay, and that is what I am going to compute. Okay. So, let us save time. So, I am going to just show you why we get this complicated expression. Okay. So, let me draw it here. So, I told you that this 2 h greater p h greater q gives me Green's function. So, we are doing from the bare function or from the free function g naught of q, and we got 2 h here, h greater p, h greater minus p, and this is h of k less. Now, h of p I again expand it. Okay. So, this one g of q is sitting here, this one g of q is sitting here, this g of q I already got. Okay. No, actually, well, I made a mistake. So, let me just change the variable. Okay. So, I am just going to write this as p and q above, this formula is written that way. So, this is p and this is q and minus q. Okay. This integral, of course, we have one term and Green's function is above. Okay. The two terms, one is this, other one is that, like this and that, but I am focusing on this one. If you know one of them, you can solve the other easily. Okay. So, this g naught of p is here, a p 4 vector. Now, how do I write h of q? So, I write to first order. So, remember it was g naught inverse q h of q 4 vector equal to, forget the nonlinear term, I am doing linear only. So, eta of q, fine. If you drop the nonlinear term, that is what I will get. So, what is h of q? H of q is equal to g naught of q eta of q, 4 vectors, correct. So, this is this term g naught of q eta of q, got it. So, this is this one. What about h of minus q? It is this term. Okay. So, this is my correction, this one. So, I got it here, and there are vortex terms, one is lambda and one is lambda p dot q, which I wrote in the previous one. You also lambda basically get something like p dot q. Okay. So, that is lambda squared and this is p squared q squared. Okay. There are some more stuff, but basically this is a sketch. Now, where do I integrate this? I integrate over a shell. This is k greater shell. Okay. So, k n plus 1 to k n, and Wilson thing it is k by lambda to k, right. Remember that. So, lambda and lambda by b, that is what I use for Wilson, but idea is to sum over a shell. Okay. Is it clear? So, I need to integrate this. Now, Green's function I already know the formula, it is 1 minus omega p q plus this p, okay, omega p plus nu p squared. So, this algebra is reasonably complex, but it can be done, and all that gives you some number integral. Okay. So, the integral, this is what we get. So, this is the term which is coming a correction nu tilde. Okay. Just trust me that, well, I have not done this calculation fully, but this is from wherever see. So, but the form looks similar, and lambda square d, why, by the why, how d is coming? D is coming because of these two etas, right, eta q, eta minus q, that is d, no, eta square is d. So, we get this d, lambda square d, and why this nu cube? So, we set basically in this, there are a lot of approximations are made. We set omega to 0, low frequency modes, large time scale, and the nu is coming. How many g's are there? 3 g's, 1 g, 2 g, 3 g. Okay. So, 3 g's gives you nu cube, that is nu cube there. And this integral will do it over a shell, and this integral will be function of lambda to lambda by b. Okay. And we can do this, but we do one more step. What is the step? I have done coarse graining right now, but following Wilson we do rescaling. So, when I coarse grain it, my boxes become big, right. I have coarse average over small boxes. So, my boxes have, instead of small boxes, I got these big boxes. So, you shrink it again. Okay. So, we in fact we want to follow Wilson scheme. So, we shrink it again, and that is a scaling step, rescaling step. A rescaling prefactor is exactly what I derived by scaling argument. It is b z minus 2. I push the system back to a small size. So, this one gives you an u less. So, this is a nu less. Okay. So, this nu less is here. So, this part b is e to power l, our standard thing which we did, e to power l, and you can expand for l small. So, it is going as 1 plus, so b to the power z minus 2 will be this one. So, it will be l times delta l times z minus 2. So, that is what I got here. Now, we substitute nu here, and b will come here. Okay. This b will come here. Okay. So, if you do all the algebra and then I get a differential equation, because this dl will come below. So, change in nu, which is you can see from here, this is original nu and this is a corrected nu with the total nu. So, the difference will give us d by d nu by dl, and this dl is sitting here, and that is the factor. Okay. So, I think I will stop here, because I think I am probably putting too much material. Okay. So, let us stop here.